Welcome back to electronics. We're starting Module 2, which is on op-amps. Our lesson objectives here are first to introduce operational amplifiers, to describe their ideal behavior, and then to introduce two particular circuits, a comparator and a buffer circuit, which use op-amps. So operational amplifiers, or what we call op-amps, are specialized circuits made up of transistors, resistors, capacitors, and they're fabricated on an integrated chip. They're actually fairly complicated internally, but the nice thing about op-amps is that they've got a fairly easy input to output sort of behavior. So if I look at this as being my input to my circuit, V sub in, and then this being the output, V out, I can come up with a fairly simple expression, relationship for the input to output behavior. So the uses of op-amps is in amplification. So I can amplify a voltage signal, make it larger, or I might be able to boost the power from the input to the output. We typically use op-amps in active filters. What do I mean by active? An active device is something that has its own power supply. So if I'm looking at this right here, V sub S, and I've got plus V sub S and minus V sub S give me a power supply. So any active element is one that has its own power supply to it. Now, another use of op-amps is in analog computers. And this is the old style computers that were used years and years ago before they had digital computers. They had op-amps in them. And that was one of the basic components of them. Let's look at op-amps in circuits. And as I mentioned, this is the power supply. These don't actually have to equal each other. I might have a different plus value and with a different minus value. And then I've got my output and my two input terminals. So actually I've got 5 inputs to this circuit. Now this circuit is fabricated on this integrated chip, and I have pins to this integrated chip that allow me to connect to the internal circuitry of it. Now common values of power supply, the V sub S, is 10 volts or 15 volts. Now a circuit symbol for an op-amp looks like this. Now I notice that I've dropped the power supply. The reason I've dropped the power supply in this symbol is because the power supply is what makes it work, but it does not affect the circuit equations that we use in analyzing op-amps in circuits. So again, the power supply doesn't affect our circuit equations in most circuits. As I mentioned, it's an active element because it has its own power supply. And the other thing is that we're ignoring that V sub S in the symbol of it. Let's first examine open loop behavior of this. So I've got my op-amp here, and I'm going to have a value A, which is a scalar of V plus minus V minus. The difference, in other words, between these two input terminals. So this A is actually the slope. And typically A is really large, say on the order of 10,000. And we often call that the open loop gain. And with that being very large, then it doesn't take very much for this to do what we call saturate, when this difference doesn't get very large before it reaches this value here where it's constant. And we call that saturation. And oftentimes, we look at the input to this circuit as Vn, and it's a difference between these two values. So this would be called Vn. So with a very small value of Vn, it saturates. Now let's do a quiz on that value. Now in the quiz, we had A is equal to 10,000, and we had V sub S is equal to 10. And so what value of this, of the voltage input before it saturated? It was 1 milliamp and minus 1 milliamp. So in other words, a very small value of Vn made this saturate. So we have what we say a very small range of operation for the linear range. This is the linear range right here. Very small range of operation when we've got what we call the open loop behavior. A comparator circuit is one that utilizes an op-amp in its open loop configuration. So we've got the open loop configuration here, and we've just repeated what this value looks like. In this particular circuit, we're assuming that for the most of the time, we are operating not in the linear region, but in the saturation region. So in other words, if Vn is greater than 0, in other words, V plus is greater than V minus, we have a value of Vs. If V plus is less than V minus, we have a value of minus Vs. So that gives us an indication whether we're looking at a difference really between these two voltages. If V plus is greater than V minus, we've got a positive value out of our comparator. And if V plus is less than V minus, we've got a negative value. So it's an indicator which of these is larger than the other. As an example of a comparator circuit, let's assume that we've got a sine wave voltage going into V plus, where C is just some constant. And we connected V minus to ground. So our input voltage is actually some constant times the sine of omega t. Now this is our comparator circuit right here, and we're assuming that C is a fairly large value, so that we're into the saturation region almost immediately as we go through 0. So if this is our sine wave of our input voltage, then we're in the linear region very, very small amount of time. So that means we're almost always in saturation. So my output will actually have a value of V sub s anytime I've got a positive value of Vn. And then when I go through the zero crossing, it becomes negative. It goes to minus Vs. And it stays that way as long as we're on the negative cycle of this sine wave. And then when we go positive again, it goes positive. So in other words, we've converted our sine wave into a square wave by sending it through a comparator. Let's examine a model or different models for op-amp behavior. Now, as I mentioned before, what's internal to an op-amp is a lot of transistors, capacitors. It's rather complicated, but we can come up with a fairly simplistic model of it that looks like this over here. And in this model, we've got what we call an input impedance, R sub I, and R sub I is actually very large. And because it's large, the current running through it is very small. So this current I is very small. And we have this dependent source right there. And that dependent source gives us the output, A times Vn, which we've already seen before, where A is some gain. Now this is a model for an op-amp. We want to come up with a simpler model. And this is what we're going to call the ideal model here. Now in the ideal model, instead of saying I is very small, we're going to say it's 0. The input current to both of these terminals, we're going to set equal to 0. And since that current is 0, in other words, this current going through this resistor is 0, then this voltage is going to be equal to 0. The voltage across these terminals is equal to 0. So this right here is equal to 0. And we've also got this equal to 0 and that equal to 0. So that's my ideal model. And we're going to use that in analyzing op-amp circuits. The simplest circuit we're going to examine is what's called a buffer circuit. A buffer circuit is made by just connecting the output back to the negative terminal. And this is what we call a feedback loop. And because it's a feedback loop, we often call that closed loop. And that's the difference. Before I used the term open loop, now this is called a closed loop. where I close the loop around here. A lot of the op-amp circuits we're going to be looking at actually have a resistor in this, but all of the other op-amp circuits we'll examine, aside from the comparator, all have this feedback loop with or without a resistor in there. Now the buffer circuit has this relationship between the output to the input. Vin is equal to Vout. We want to examine how you come up with that equation. And to examine that, it's actually easier to redraw this circuit showing some sort of reference ground, because this Vin is a node voltage and it's with respect to some ground. So let me go ahead and redraw the input and the output voltages this way, because I want to do a KVL around this. I'm going to do a KVL from the ground up across the input of the op-amp, and then back to the output. So this is back to ground, so I've done a complete loop there, and I want to show these equations. The way I do a KVL is I will go to here. When I see a negative sign on an element, I add in a minus voltage and going around. Now, actually, when I go from here to here, I'm gaining potential, and I come around here, I'm losing potential. But just for my sake and a lot of students' sake, it's just easier to use the convention. Whenever you come to a minus sign, subtract it. Whenever you come to a plus sign first, you add it. So coming across here, I have the minus Vin, and then I've got the voltage drop across this input. Well, with the ideal op-amp behavior, that would be 0 volts. And then coming around here, I get to the plus Vout is equal to 0. And that gives me the equation back for a buffer circuit. So in summary, we've shown that op-amps are active devices, active again meaning they've got their own power supply, and they can be used to filter or amplify signals linearly. Let me make just a comment about what I mean by linearly. We've got an input and output characteristic. And in the open loop, we showed that we've got this range right here before we saturate. This range right here is what we call the linear range. So if we stay in that range, we stay in what we call a linear range. Now we looked at ideal op-amp models. In particular, the model required this assumption. So any of the following lessons, we will be developing a lot of op-amp circuits. We will always go back to this model right here where these assumptions are true. We looked at 2 particular types of circuits, a comparator circuit and a buffer circuit. So the remainder of Module 2, we will go in more depth in the buffer circuit. We will cover a number of different amplifier configurations with op-amps, and we will look at differentiators and integrator circuits, and then we'll go on to look at active filters. Now, I'd like to encourage you again to go to the forums and ask and answer questions. We really appreciate your participation, especially those of you who are on there answering questions. You do a great favor to us and to the rest of the class. Thank you.